Today we are making a realistic and cinematic Saturn in Blender that renders with minimal samples. Start with a cube, subdivide it a whole bunch, turn it into a sphere, Shift, Alt, S, and then 1. Make sure every dimension is equal to 2, and apply all of your transforms. The Z dimension should be equal to 1.80408. Make sure to apply all transforms again. This is our atmosphere. Duplicate this atmosphere and rename it cloud layer. Give the cloud layer a new material and just set it to black. Give the atmosphere a new material. Grab a geometry node, plug the position into the volume and displacement, set the step rate to 0.25 and set it to displacement only. We need to displace this volume off of the cloud layer by an accurate factor. So I've already done the math and scaled everything for you. So assuming, the equatorial radius, which we don't have to assume because it is, in this case, because I've scaled it down, is 1 meter. That means this should be scaled by 0.001975. Grab a value, and copy this into here, group this. We will call this output height, and call this node atmosphere height. Now we need to calculate the distance from the center to the edge, or separating the XYZ components of the surface normal. Then we are dividing by our planet dimensions, which is 22180 or 1.80408. Rename this vector dimensions. Call this node planet dimensions. Separate the X, Y, and Z components. Divide this by 2. So X, Y, and Z, all of these components. We recombine each X, Y, and Z component, and then we get the magnitude of these vectors. So we can group these distance, the surface normal. Call this node distance to edge. Then this will normalize the radius. Subtract a 1 meter radius. Duplicate this atmosphere height. Make a new user. Normalized planet radius. Then set a maximum of 0. Then we divide by the atmosphere height to get a normalized scale from 0 to 1. Then we multiply by -1. And then we can multiply by the gravitational acceleration on Saturn. It's about 11.19. We'll make a new user for atmosphere height. Call this mean gravitational acceleration. And it's e, our natural logarithm, to the power of this function that we've just written, and then we divide by the atmosphere height. Multiply by the air density. The air density in kilograms per meter cubed is about 0.19 on Saturn. That's 1 bar air density. So let's just group all of this. We can call the density. Call it simple. Alright, this is the simple barometric formula. Take a RGB node and just set it to around this color. That's around Saturn's atmosphere color. It's got a very Earth-like atmosphere. And group this. We'll just call this color. This is the atmosphere color. Now if we plug this in, every volumetric medium, for example, this one, terminator line would probably be around here, and the light direction is coming from here. Atmospheric scattering is very wavelength dependent. Blue is a shorter wavelength. Red has a relatively long wavelength. Because of this, red can travel a longer distance through volumetric mediums without depleting. Which is why sunsets look red, is because it has to travel through more volumetric medium here and eventually get to the terminator line, which is when all of the light decays, the planet shadows the atmosphere, and all red light and blue light ends up getting absorbed, and green light, etc. But blue light can't make it all the way to this, so around here it starts scattering red light in this area. So that's a part we'll end up doing later on in the video, using a custom lighting computation kind of engine in the nodes. Pretty much it samples a texture or samples some sort of density, and then it moves it along a vector like the light direction, resamples, moves it along, and just continually adds it up. And that's kind of a a very basic verbal rundown of how the engine works, and then it just keeps on adding up all this data until we get to the terminator line, and then we get shadow. We still need to calculate the absorption for this. So we can add absorption. So what we're going to do here though is separate the x, y, and z components and just multiply all of our components by -1. Then it's Euler's number to the power of these negative components, and then we just recombine these. So we're going to group this all together. Plug these vectors into the inputs and outputs, and then set them as colors. This will be color in, or sorry, color out and color in. So we take our atmosphere color and take the extinction, multiply it by our barometric density. So this ends up being our emission, or our scattering color, and then this is our absorption. We need to normalize this, and then get the length or the magnitude of this, plug that into our density. We'll group this entire thing here. This is going to be primarily Rayleigh scattering. Go ahead and pull this Rayleigh from here, and then we'll make this lighting engine. Grab a vector math node, and we need 3 vectors on each side, and we need a color on each side, and then we need 3 floats. So just grab a value. We need 3 of these on each side. Surface. And just do the same for the other side. We're going to have around 5 of these samples, so I'll just call this lighting sample, and let's just chain 5 of these together. So we've chained 5 of these together. The way this works, I was talking about, you are taking some sort of density or texture and you are adding to, you are moving it along a sampling vector. So that's this sampler in. For now we can just scale by 1/5 the amount of samples we have. Right now we can just assume our sampler is equal to 1 on the x-axis, and our surface normal is its position. Position technically is actually the viewing position, viewing direction, which is the incoming actually. So we'll plug that into there for now. This I usually like to set to 3, and this progressive render, this is white noise that it adds with each sample that it takes. So we just plug this into there, and then value into this. Plug extinction out into this color. There we go. So we take this and then plug the surface normal into here. And then we take this. Okay, so here, what this is doing, surface normal, the position, assuming it's starting at, 0, 0, 0, we are moving it along 1 on the x-axis, right? But that 1 is multiplied by 0.2 or divided by 5. So it's moving it, 1/5 of the way across here, away from the direction of the light. The light direction is facing this way. So we don't want to just resample this 5 more times, because that sample won't be moving at all. So when we move this sample over, the sample point, we want to reuse this as the surface normal, so that way when it feeds in here through the next one, it's moving it by another fifth. And then on the third fifth, it's moved it by 3/5, 4/5, 5/5. You can imagine the rest. Actually, that is the rest. There's 5 samples. So we need to utilize this already added surface normal. Plug that into the next one. This position just goes into here, and these all plug directly into each other, except for the progressive renderer. We can plug something into here right now. Anyways, 1 plus progressive renderer, that goes into this one. We're not going to be using this right now. Later on, when we're done the rest of this sample, we will. So we also scale this, the absorption, by the length of the scaled sample. Just because we're not scaling by a full one, it's scaling by 1/5. We need it to always equal 1 at the end. So something like this. And then this scale just plugs directly into the extinction and the sampler. The sample is also, it's just this. So we can go ahead and preview this right now. It's not going to be correct. This sampler is not exactly what we need. We're going to use a ray sphere intersection function for this. Let me just delete these annotations. We're going to use a ray sphere intersection function because it's a sphere, first off. And, you know, we need to define boundaries of where these rays towards the sun, because we're marching towards the sun. We need to define boundaries for where these rays intersect, so we know exactly where to calculate. Because right now it has no idea what we're trying to do. We're just moving a density along a vector additively. There's another problem where, you know, we don't have the thing where we are. Well, first off, we're not using our progressive render, and also it would be quite harsh, like very harsh lines right now where we just have 1/5. We're adding 1/5 each single time. We need some sort of smoothing between those samples. So what we can do, make sure this is still plugged into progressive renderer, but what we can do is this divided by the quality to the power of the computation proximity minus quality divided by, oh wait, sorry, the progressive renderer divided by the quality, or the amount of samples, and then this 2 to the power of our computation proximity, and we plug this into our scale. Look at that. Still not correct, like we've already stated, right? We haven't defined bounds for the intersection points in the atmosphere. So I'm just going to link a Google Drive to a ray sphere intersection function, and I'm just going to append mine. Okay, so I've got my ray sphere intersection function. Our radius will be our normalized planet radius plus our atmosphere height, because this is our radius, right? The entire thing. And then we have this surface normal and our sun direction. Our sun direction we don't actually have a node for yet. Unless, did I accidentally like bring that in here? No, okay. Yes, so we need a sun direction. Actually, we can just reuse the planet dimensions. We'll make a new user and then call this sun direction. We'll do like 1 and hold on, let me check. What did I do for mine? Okay. Here, we'll go over how to kind of recreate the thumbnail. So negative 0.35, so it's pointing up a little for the Z. Technically this is the Y, but you know, Blender's a little weird. Right. So we plug this in the sun direction and we normalize our surface normal. Then we subtract close from far. Plug this into sampler. Ah, right. Sorry, I've forgotten a very crucial step. Because this is additive, we need to add the extinction from the previous sample. And look at that. Pretty neat stuff. So we can plug this. So we just multiply this color by our extinction. Plug this into here. And look at that. We have an atmosphere. And group these. So whoops, that wasn't supposed to do that. Yeah, we don't need this position. Okay. So this is the surface normal. And this will be our lighting computation. You look at that. So we've got a lighting computation for our atmosphere. We're missing a few things though, you know, like the cloud layer. We can add this in now. Yeah, sure, why not? So grab our lighting computation and our geometry node, plug position into here, incoming. I'm going to grab my Saturn texture. What we do is we take our air density and we go ahead and multiply this by 1,000. That's what we multiply this by. Then we multiply by our lighting computation. Because this is a gas, this will also be plugged into the volume. Volumetric mediums will absorb and scatter the same wavelengths of light. So we need to calculate the absorption, which is pretty easy. Blender has a built-in node that can do this. And then from here, we can just normalize this, plug that color into here. Whoa. Plug that color into here. And we can take our extinction node. And then we can grab the magnitude of that vector, plug this into density. And there we go. Right here we'll be using a circle. Set the vertices to 256. The radius will be about 1.2323 for the inner radius, with an outer radius of 2.65481. We can join these together and bridge edge loops. Rename this material rings, geometry node, and we're going to grab the position, grab the length of this position, and we're going to subtract the inner radius. Let's make this easier on ourselves because we'll need to use these variables a few times. So we'll call this inner ring radius, and we need an outer ring radius. Remember, the outer ring radius is equal to 2.65481. So we subtract the inner radius from this length. Oops. And then we simply just divide by the outer radius minus the inner radius. We can use the image texture now. I do not use an environment for this. I will grab my ring texture, and that should be correctly mapped along the entire thing. We get the length or magnitude and multiply by our ring density. So we'll say 75 is our ring density. Mix shader, and this is a factor between two different types of shaders, which is a transparent BSDF on our first slot, and the rings in the second. What we can do here is actually use an emission, and this is our color. But you'll notice it does not cast accurate shadows on the rings. A planet, doesn't just have shadows cast on it by its rings. The rings have a shadow cast on it by its planet's host. So, so I've got my phase function here. I forgot to mention, your sun direction needs to be normalized. That just caused me like 7 minutes of troubleshooting. That was so unnecessary. This needs to be normalized. And this should be called direction. Yeah, there we go. That's interesting. 1 plus our phase function. That's what we're multiplying our rings by. Then you can see what's going on here. And something seems a little funky. I don't know what it is. Oh, I know what's wrong. This is 3/2, not 3/4. There we go. There we go, shimmer. Check that out. We grab our sun direction, and here, sorry, let me just clean up recursive data blocks. So, we grab our sun direction and dot this with the position. We get something like this. Then it's just kind of 0 minus this. We set a maximum of 0, so it doesn't go below 0. And a minimum of 1. We're just completely clamping this. Then we need to multiply this. Or here, we grab our ray sphere intersection function. Our radius is our normalized planet radius, which is just 1. Our sun direction being our sun direction, and our surface normal just being our surface normal. We're given these vectors. So, like usual, we subtract these, and then we've got this kind of thing going on. So, you can see how this changes as we change the sun rotation. Which is interesting. Then we grab our distance to edge. And set a minimum of 1, so it does not go above 1. We multiply these together. Then we multiply our... Actually, you know what? No. We'll multiply by -1, multiply by our air density times 1000. So density at 1000 bar. and then e to the power of this. There we go. Then we can just multiply this together. And then we've got rings with a planet shadow being cast onto them. And this is a ray plane intersection function. So our surface normal is the position, our sun direction being just our sun direction, plane origin and plane normal. Plane normal is just the rotation of the ring, normalized rotation of the rings in radians. That's what all of these vectors use, like the light direction. So we get the length of this vector. If we plug this into here, we'll be able to see what's going on, right? So we get the length of this vector, and we can actually just kind of steal something from something else we just did in the rings. If we borrow this, here we go. There we go. So that is where rings will and won't be mapped. So now we use this to map our ring texture. Set this to clip just so we can see what's going on. Grab the length of this. We're going to multiply by this value, multiply by our ring density. Make sure this is negative as well, because we're going to be using a natural logarithm. Then e to the power of this. There we go. Pretty neat. So then we just use this to multiply, and you can see where that will be. So what we can do, just copy this over to the cloud layer, plug the position into here, scale by this. There we go. Realistic and cinematic Saturn, completely done in Blender, with a custom lighting engine, and some other neat little things going on. And yeah. And if this atmosphere looks too dense, which it is, you should be able to see a bit more of the yellow from the surface, or sorry, the gaseous material underneath. Well, definitely decreasing the step rate helps. But you can also just take the atmosphere color and darken this till you're content with it, and then there you go. Okay, actually, and now that I look at it, those ring shadows are a bit dark. We could probably put this ring density at like 50. Because these, yeah, there we go. Maybe even 42. Yeah, so something like this. You put your camera here. And that's how to make cinematic Saturn in Blender. Enjoy experimenting around with this. Ask any questions in the comments. Recommendations for next video. Goodbye.